Next we discuss pH of the hydrolyzed salt solution. The dissociation of the weak acid HX is given by, this is dissociation constant is concentration of H plus times concentration of X minus by concentration of HX. So from there we can actually calculate concentration of H plus. So concentration of H plus is Ka times concentration of Hx by concentration of X minus. Now concentration of H plus is Ka times H. H is the again hydrolysis constant, so we can write Ka times root over Kh, and we can further simplify this one by substituting the value of Kh. So we get Ka times square root of Kw by Ka times Kv, and so we get basically is Kw times Ka by Kv. That is the relationship. Now pH is minus log of concentration of H plus. So if we take log of H plus ion here, we get pH. pH is minus log Kw times Ka by Kb square and raised to the half. So if we further simplify this one, we get minus half log Kw and then minus log Ka plus half log Kb. But we know that minus log Kw is pKw and minus log Ka is pKa and minus log Kb is pKb. So pH will be half of pKw plus half of pKa minus half of pKb. And at 298 Kelvin temperature, the value of pKw is 14, that we already know. So pH will be half times 14, so it will give 7 plus half of pKa minus pKb. Next we discuss salt of strong acid and strong base. So in this case, the cation neither the cation nor the anion undergoes hydrolysis. Therefore, the resulting solution is neutral. Example of these are aqueous solutions of KCl, because KCl is formed by strong base KOH and strong acid HCl, NaCl again formed by NaOH and HCl, etc. When dissolved in water, the ions K plus and Cl minus have no tendency to react with the H plus and OH minus ions of water. This is because the possible products of such reactions are KOH and HCl, which themselves are completely dissociated. As a result, there is no change in the concentration of H plus and OH minus ion, and therefore the solution remains neutral. Next we discuss some problems related to this topic. The first problem is write the conjugate acids and bases for the following. So first we write the conjugate acids. So for OH minus, the conjugate acid is H2O, right? For HCO3 minus, the conjugate acid is H2CO3. For CO32 minus, the conjugate acid is HCO3 minus, and for CH3 COOH, the conjugate acid is CH3 COOH2 plus. And next we discuss conjugate bases. For H is minus, the conjugate base is S2 minus. H3O plus, the conjugate base is H2O. HSO4 minus, the conjugate base is SO4 2 minus, and H2PO4 minus, the conjugate base is HPO4 2 minus. Problem number 2 says classify the following into Lewis acids or Lewis bases. So OH minus is Lewis base because it can donate a pair of electrons. F minus. Again it acts as Lewis base because it can donate electrons. Next is H plus. Lewis acid, as it can accept a pair of electrons. BCl3, again it acts as Lewis acid because it is electron deficient, that you already studied. Next problem says the pH of a solution is measured to be 4.4. Determine the concentration of H3O plus and OH minus. So here pH is 4.4. So we know pH is nothing but minus log 10 base concentration of H3O plus, right? So we write minus log 10 base H3O plus is 4.4. So we get log 10 base H3O plus is minus 4.4. So we get concentration of H3O plus is 10 raised to the minus 4.4. Okay. So that is the concentration of H3O plus. Okay. So if we further simplify this one, okay, so we get basically concentration of H3O plus is 3.98 times 10 to the minus 5 moles per liter. Now we know Kw is concentration of H3O plus times concentration of OH minus, right? So we get concentration of OH minus like Kw by concentration of H3O plus, and the value of Kw we already know is 1 times 10 to the minus 14 considering 298 K temperature. T equals to 298 K by concentration of H3O plus is 3.98 times 10 to the minus 5. So we get concentration of OH minus is roughly 2.5 times 10 to the minus 9 moles per liter. Not minus 9, it is actually minus 10. Okay, so this is 1, so this is minus 10. Next we move to problem number 4. It says calculate the concentration of hydronium ion and hydroxyl ion in 0.0 molar HCl and 0.005 molar NaOH solution. So HCl, first we discuss about HCl. So HCl completely ionizes because it's strong acid, ionizes as HCl aqueous plus H2O liquid gives H3O plus aqueous plus Cl minus aqueous, right. Now the concentration of hydronium ions means H3O plus is equal to that of HCl, right, because it completely ionizes here. So, concentration of H3O plus is concentration of HCl, and this is equals to 0.01 molar, or you can write 1 times 10 to the minus 2 molar. So, concentration of H3O plus is 1 times 10 to the minus 2 molar. Again, the ionic product of water means Kw is concentration of H3O plus times concentration of OH minus is 1 times 10 to the minus 14, right, at 298 K. So, concentration of OH minus is Kw by concentration of H3O plus. So, we get 1 times 10 to the minus 14 by 1 times 10 to the minus 2. So, we get 1 times 10 to the minus 12 molar. So, or moles per liter we can write. Okay. So, this is for HCl. Now, we talk about NaOH solution. Okay. So, for again NaOH is a strong base, so it will again completely ionize. Okay. So, NaOH completely ionizes as NaOH aqueous gives Na plus aqueous plus OH minus aqueous. Right. Therefore, or since concentration of NaOH aqueous is equal to concentration of OH minus aqueous, therefore, concentration of OH minus will be 0.005 molars, or you can write 5 times 10 to the minus 3 molars. So, this is the concentration of OH minus for NaOH. Again, we use the ionic product of water. Again, the ionic product of water Kw is concentration of H3O plus times concentration of OH minus, and the value is 1 times 10 to the minus 14 at 298 K. So, concentration of H3O plus is 1 times 10 to the minus 14 by concentration of OH minus. So, we get 1 times 10 to the minus 14 by concentration of OH minus is 5 times 10 to the minus 3. So, we get concentration of H3O plus is 2 times 10 to the minus 12 moles liter inverse. Problem number 5 says the pH of a blood sample is 7.4. Determine the concentration of H3O plus and OH minus ions. So, given the pH of a blood sample is 7.4, right. So, minus log of 10 base concentration of H3O plus is 7.4. So, concentration of H3O plus is minus 10 to the 10 raised to the minus 7.4. So, if we calculate this one, we get concentration of H3O plus is approximately 4 times 10 to the minus 8 moles per liter. So, this is the concentration of H3O plus. So, again if we use like before that ionic product of water here also. So, again the ionic product of water Kw is concentration of H3O plus times concentration of OH minus, and the value again is 1 times 10 to the minus 14 at 298 K. So, we are considering 298 K temperature. So, concentration of OH minus will be Kw by concentration of H3O plus. Now, we put the value of H3 plus here. So, numerator will be 1 times 10 to the minus 14 and the denominator will be 4 times 10 to the minus 8. So, we get concentration of OH minus is 2.5 times 10 to the minus 7 moles per liter inverse, moles liter inverse. Problem number 6 says calculate the hydroxide ion concentration in a 0.1 molar solution of ammonium hydroxide given that Kb is 1.8 times 10 to the minus 5. So, here ammonium hydroxide is a weak base, right. So, we need to calculate concentration, okay, using the value of Kb. Okay. So, ammonium hydroxide NH4OH is a weak base. So, NH4OH dissociates as NH4OH aqueous is NH4 plus aqueous plus OH minus aqueous. Now, Kb is product by reactants. So, concentration of NH4 plus times concentration of OH minus by concentration of NH4OH, right. Okay. So, can I now concentration of NH4 plus equals to concentration of NH4OH and so we can write, and concentration of OH minus is 0.1 m. So, we can write Kb, sorry, concentration of NH4 plus is concentration of equals to a concentration of OH minus here. Okay. So, we can write Kb is concentration of OH minus raised to the 2 by concentration of NH4OH. Okay. So, this is the value of Kb. Now, what we do, we use the value of Kb. Okay. So, concentration of NH4OH is given. Now, again concentration of NH4OH is given, right, is 0.1 molar. So, the value of Kb is 1.8 times 10 to the minus 5 and concentration of OH minus raised to the 2 by concentration of NH4 is 0.1 m. Okay. So, we can write concentration of OH minus raised to the 2 is 1.8 times 10 to the minus 5 times 0.1. So, we can write 1.8 times 10 to the minus 6. So concentration of OH minus is square root of 1.8 times 10 to the minus 6. So we get roughly 1.34 times 10 to the minus 3 moles liter inverse. Okay, so this is the concentration of hydroxide ion. Next we discuss problem number 7. It says at 298 K the solubility of SrOH2 is 19.32 grams per liter of solution. Determine the concentration of strontium and hydroxide ion as well as the pH of the solution. So first we need to calculate the molar mass of SrOH2, right? So the molar mass of SrOH2 is 87.26 plus 87.6 plus 16 plus 1 times 2. So we get 121, roughly you can consider 121.6 okay, grams per mole. So this is the molar mass of SrOH2. So if we consider only 87, that is also fine. So to make our life simpler, so we write 87 plus 16 plus 1 times 2, so we get 121 grams per mole. So the molar solubility, so concentration is nothing but molar solubility. So we have used 19.32 gram. So what is the molarity of the solution? So 19.32 by 121. So it gives us 0.1581 moles. So this is the number of moles present. Okay. So now we need to consider the ionization of SrOH2. Okay. So SrOH2 ionizes as Sr2 plus 2H minus, right. Now concentration of Sr2 plus is 0.1581 mole, that we calculated just now. Okay, so 2 times concentration of OH minus is 2 times 0.1581 equals to 0.3162. Right. Now, so this is the concentration of OH minus here, right. So concentration of OH minus is nothing but, because 0.1581 mole SrOH2 gives 0.1581 mole Sr2 plus and 2 times 0.1581 moles of concentration of OH minus. So we get concentration of OH minus is 0.3162 mole. Again, considering Kw is concentration of H3O plus times concentration of OH minus is 1.1 times 10 to the minus 14 at 298 K. So we get concentration of H3O plus is Kw by concentration of OH minus. So Kw is 1 times 10 to the minus 14 and concentration of OH minus we just calculated 0.3162. So we get concentration of H3O plus. Okay, so if we do it, we basically get the value is 3.163 times 10 to the minus 14. So the pH, again pH is minus log 10 base concentration of H3O plus. So minus log 10 base 3.163 times 10 to the minus 14. So, if you carry out this one, we get the value of pH. So, pH is 13.50. Okay, so therefore, the pH of the solution is is 13.50. Next, we move to problem number 8. It says calculate the percent ionization of 0.20 molar solution of hydrocyanic acid HCN. So, acid dissociation constant Ka is given. Okay, so HCN is weak acid, right? So, HCN dissociates as H plus plus Cn minus, right. Now, initial concentration is 0.20 mole. So, initial 0.20 and initially there is no H plus and Cn minus, and at equilibrium 0.20 minus alpha. Alpha is the degree of dissociation. So, we get alpha and alpha. Okay. So, here alpha is degree of dissociation. Dissociation of HCN. Okay. So, Ka is concentration of H plus times concentration of Cn minus by concentration of HCN. So, at equilibrium the values are alpha times alpha, sorry, this is 0.2 times, okay. So, this is not correct, this is 0.2 in 1 minus alpha. So, here you get 0.2 alpha, this is also 0.2 alpha. So, 0.2 alpha you get, so you get 0.2 alpha times 0.2 alpha by 0.2 times 1 minus alpha. So, now you substitute the value of Ka. Ka is 4.9 times 10 to the minus 10 is 0.2, they cancel each other, you get 0.2 times alpha by 1 minus alpha. So, you can actually write 0.2 alpha by 1 if considering alpha is very small compared to 1. So, we can write 1 minus alpha is nothing but 1. We can just ignore alpha here. So, you get alpha is 4.9 times 10 to the minus 10 by 0.2. Okay, so, we get 0.2 alpha square here. Okay, so, alpha is square root of this we get, and if we calculate this one we get this is 4.95 times 10 to the minus 5. So, this is the value of alpha. So, we need to calculate percent ionization. Okay, so, therefore, the percent ionization is is 0.00495%.